Okay, so now we are continuing our discussion about GPS field applications. This is the second GPS video, and if you have not watched the first one, please do so. The order does matter. So right now what we're going to do is, now that we understand a little bit of what constitutes GPS and what it is, let's talk about a little more about how it works in the survey world. So first of all, let's acknowledge the fact that the Earth is not indeed a perfect sphere, but is instead an ellipsoid. An ellipsoid is formed when an ellipse is rotated about its minor axis. A geoid, let's talk about, that's a new word maybe. A geoid is defined as a hypothetical figure representing the shape of the Earth that coincides exactly with the mean sea level. So these two appear to be the same thing, but are in fact not at all. Actually, I have a good picture that'll help you visualize what I'm talking about. So we have here a bunch of different things, and let's take a minute to figure them out. This shape is an ellipsoid. It's the approximate shape of the Earth. Then we have this called the geoid surface, which is the mean sea levels. So once you take the shape of the Earth and you check where the sea levels are, you actually then have Earth or ground surface, which I know it appears like this half the Earth, and you clearly, this can't be wrong. But just imagine everything's been kind of super uber exaggerated. So this distance between the Earth or ground surface with the ellipsoid is called the height above the ellipsoid. And this line down here, this height right here is the height above mean sea level of the Earth's surface. So there's all kinds of stuff going on. So how does a GPS even think about looking at the Earth? So what does this mean to us? We have mostly ignored the shape of the Earth in our calculation, and as I mentioned in the previous video, distances were not long before because this is a plane surveying course. But with GPS, that does not have to be the case. We can actually measure things that are far, far, far away from each other. Okay? Okay. All right. So what do we need to know? We need to know the elevation of a particular point given by GPS, which will be the height h, and that from that to a point from the surface of the ellipsoid to the point in question. So surveyors need the height h above or below mean sea level so that they can actually start computing, and the GPS kind of knows what it's supposed to do. So let's think about this for a second, and I'm trying to think of what else is relevant here, but I might have it. Here's a video, and actually, let me click, let's see if we can watch what's going on. It's actually really not the most exciting video or the best produced video ever, but I did find one of like this one guy working with a GPS by himself and setting it up and doing everything, and we'll get to see this live hopefully someday, or maybe you already have, but yeah, just something to keep in mind. So I won't show you.
Hey guys, it's Chris with the Gorilla Gunfighter, and today I'm going to show you what I do for a job. I'm a land surveyor, and so there's not going to be no explosions, no guns, no knives, no killing stuff, so if that's what you're looking for, I'm going to check somewhere else. But if you want to learn how to set up a GPS page...
I'm just going to... Okay. So he's showing all the equipment. Again, I'm not going to play 21 minutes worth of video. I just typed, I think, land survey, and this came up, and basically this guy in 20 minutes is able to set this up. And basically, look, there's a lot of the same stuff that we've covered in this class, setting the tripod. Now this is new, we don't have this. This is the fancy GPS unit that costs more than I make in a year, or more, several years. Anyway, so he connects a bunch of stuff, a data collector and whatnot, and make sure it gets online and that it locates at least a certain amount of satellites. And once that happens, he's gonna go, he's setting up an antenna. And then he's gonna grab the, I blanked on the name, but anyway, basically, he's gonna stand at different points with a prism, there we go, and yeah, well, no, actually with the receiver. I'm thinking of total station when I say prism. The receiver, and is gonna walk around and like, just capture points. It's really awesome, okay? Well, back to reality. So it's called Land Survey by Buckshot University. Has a lot of views. There's a lot of good videos on surveying. Anyway, let's continue. So anyway, it is common practice to use GPS to locate control points and then use traditional surveying measurements to determine the location of other points with respect to these control points. So one thing that's worth noting is just because you have a GPS and you can use a GPS doesn't mean you need to use a GPS every time for everything. There are reasons not to, and again, sometimes you're inside, sometimes it's a deep forested area, or sometimes you just, I don't know, don't have the right equipment or something. And if you know the exact location of one point, it's kind of like having the benchmark information, but more precise even, and then going from there. Actually, benchmarks nowadays are taken with GPSs by United States Geological Survey, USGS, yes. But anyway, let's see. So there's different types of GPS. I'm not talking about the actual machine, I'm talking about the method. So static GPS is when one receiver is placed at a point whose coordinates are well known and the other receiver is placed where the coordinates are desired, and this provides excellent accuracy. So this is common, what's most commonly used. On the other hand, we have kinematic GPS, which is when you collect positions while the GPS is in motion. And for this to work, the roving receiver must be able to lock into at least 4 satellites, and this lock must be continuously maintained. Okay, a lot trickier, but doable. Okay, so if we need at least 4 satellites so at least 4 satellites are visible at any one time, and each satellite is visible from a location for 4 to 6 hours. Okay, because remember the system has 24 or more satellites. So right now, if you look up at the sky, you can't see them with your bare eyes, unless in a really clear night, sometimes you can see them moving. It's kind of cool. But there are at least 4 satellites on top of you, and they will remain on top of you for 4 to 6 hours. The symmetry of the satellites will control the level of precision. So depending on the time of the day and your location, sometimes it's a good time to survey, and sometimes it is not a good time to survey. So how do we know? There are these symmetry factors that you can calculate. One is called the GDOP, which stands for geometric dilution of precision. The other one is called PDOP, which is the positional dilution of precision. And VDOP, which stands for the vertical dilution of position. And all of those are metrics that show you if it's a good moment to, if the satellites are in a position and you're in a position in which the satellites can do the best and most precise job possible. So this is something that is actually not so hard to calculate, but here's the good news. Well, it's actually very complicated if you get into all of the math of it. But what I'm talking about, these metrics like GDOP, PDOP, VDOP, are simple, and most GPS satellite systems, GPS like surveying systems, can calculate these things automatically. They just get turned on, they kind of go online, and they can tell you if the satellites are in a good spot and how many it's locating. So here's a good example. This is poor positional dilution of precision. All the satellites are close to each other, and you're like, how is that possible? Well, sometimes that happens, depending, again, the time of the day. Remember, they're rotating in different orbits, so sometimes it can coincide like that. How the planets align every once in a while, so do satellites. And then good PDOP would have a good distribution. It doesn't have to be perfectly symmetrical, but if it is a little more, if you have better angles between these, the triangulation of the exact measurement will be much, much, much better. Okay, so something that helps surveyors, and again, your GPS unit can do this, but the idea is that the predicated accuracy of a particular measurement is going to equal something, the PDOP, which the PDOP, you'll just see it, it's going to be this number, and it's calculated internally by the, once the GPS unit knows where the satellites are. And basically, you have all of these different types of errors that have, like you can say an anticipated error. You know that this is the approximate error for these different types of things that could happen. And the way that you would calculate this is you would get the, you know how to get a, what is it called? Root mean square, of course. The root mean square means you take the square root of all of the different measurements squared. So it's really not hard. So basically, if I want to find out what the error is going to be on my measurement, I would go square root of 12 squared plus 1 squared plus, go away Skype, plus 4 squared plus 5 squared plus 2 squared, which is actually equal to, let me see, 13.784. And then you're actually going to multiply this. So this is called the RMS, root mean square, and then times the PDOP, which in this case it's 2, so times PDOP, that's supposed to be a P, times 2, which in this case gives me 27.568, and depending on what you're surveying, that you would know what number would be acceptable. But it's actually easier to figure out that the PDOP, when it's 1, it's as good as it's going to get. It's kind of like at its best. If it is equal or greater to 5, I'll put it like this, then try later. So it means right now it's not a good time to do the survey. You're going to get a huge, because imagine multiplying this number, the difference of multiplying it times 1, times 2 versus times 5, right? So, yeah, okay. That's all the fancy math you will do for this chapter, by the way. Okay, so a lot hinges on the precision of the GPS. A lot of money has been spent perfecting this system. So data about GPS accuracy is available to you via a sky plot. So a sky plot is something also that you can access online and will know at all times of the day from different positions. Basically, it has this combination of graphs and elevations and vertical angles that will tell you these metrics. Your GPS will be able to tell you some things, but this sky plot is actually a lot more efficient at that. So you can use skyplot to plan times in which the satellites will be at their optimal positions before you head out. So instead of heading out and being like, oh no, I came all the way over here and I set this up and turns out it's a bad time, instead you can look at the skyplot and they can kind of calculate when a good time will be depending on the position of the satellites and your position on Earth. Okay, in the next video we're going to talk about GIS, so stay tuned.